All right, so first, in looking at graphing a log that's the inverse of a growth function. If you were to look at the graph of a growth function looks like this. Okay, so this is the graph of y equals a times base b to the power of x when b is greater than, the absolute value of b is greater than 1. That's going to determine that you're dealing with a growth function. Okay, and what we're going to base this graph on is the idea that when you create an inverse, the inverse of a graph is going to reflect it's going to be a reflection of a graph across the line y equals x. So this green line right here is the line y equals x. Anytime you're dealing with an inverse, the inverse is just the graph reflected along this path. And if you think of what an inverse just exchanges the x's and y's of one function. So here, if I wanted to sketch my actual parent graph of this log, I'll take this point because I can see what it is. But this is the point 0, 1. So if I exchange the x's and y's, it becomes what? The 0, 1 becomes 1, 0, right? So when I exchange that, this becomes the point 1, 0. And as you can see right here, this portion of the line, when we reflect it across this green line, y equals x, comes down and approaches the bottom here. And then this portion, this upper portion of the growth function, is going to be reflected along that green path in this manner. Okay, so this red graph right here is the parent function that we're looking for, a times log base b of x. And again, what designates this as the inverse of the growth function is that the base of your log, so b, the absolute value of that, it fits the same conditions as it would on a growth function. It's greater than 1. Okay, so this red graph is our parent function. When your log has a base that's greater than 1. Okay, now, as far as the pieces of information that you can take away from this is the following. For logs, there's no horizontal asymptote. The horizontal asymptote exists for exponential functions. So HA means horizontal asymptote. There's going to be none. The vertical asymptote is just going to be y equals 0. So again, this, we exchange the x's and y's. So in the growth function, the asymptote was y equals 0. So in the log function, it's going to be x equals 0. So this is your vertical asymptote. And really, it's going to be affected by the horizontal shift of your graph. This number will change based on the horizontal shifting of your graph. So the vertical asymptote is just going to be the equation x equals whatever the horizontal shift is. Okay, when we look at the domain and range of this graph, again, the domain goes from left to right. When you look at this, the furthest to the left point extends all the way to, but not past, our vertical asymptote. So it goes from 0 and it extends to infinity. Again, it doesn't actually reach that value of 0. So again, whatever the horizontal shift is going to be that limiting factor to your domain. The range goes from the ground or from the bottom up. And what you can see here is there's no limit to the lowest y, no limit to the highest y. And so the domain or the range is going to be all real numbers from negative infinity to positive infinity. Okay, you're also going to have to identify left and right behaviors. Hey, when you identify the left and right behaviors, there's something a little bit more specific again with this, because when we find the inverse of a decay function, the left behavior, it's going to approach the asymptote in both of those, whether it's growth or decay, but you have to be able to determine whether it's approaching it in the downward direction or in the upward direction. So here the left behavior of this graph is it's moving down to the asymptote. Okay, so it is approaching the asymptote, but it's doing so as it falls. Okay, and then the right behavior here is it is going up or rising to the right. Okay, the final piece of information that you need to be able to identify on these graphs is going to be an x-intercept. Okay, and so for the parent function, the x-intercept is just 1, 0. Okay, and depending on what your function looks like, you have to solve for this x-intercept, and I'll show you that in this next example. Okay? But these are your just generic properties of your parent function when you're graphing the log that is the inverse of a growth function. Emma? It says x-intercept is 1, 0. All right, questions on this? These are just kind of the general tendencies for this graph. I'm going to go through one example and have you guys do another example. Okay, so I want you to see, or I want to talk through how you would graph the following. All right. So here we're going to look to and go through how you would graph this log. All right, so the first step is you need to determine whether you are dealing with a log that's the inverse of a growth or the inverse of a decay function. And so far we've only talked about the 1. Okay, so when we look at the base of this log, is this a value greater than 1? Yeah. So this is going to be a function or a log graph that's the inverse of a growth function. So if we took our parent function for our growth model, again, the parent function looks like this. Okay, so here's the function that we're going to be basing this off. Okay, and let's go through and answer these questions. Is there any vertical shift in this function? Anything being added or subtracted outside the function? Yeah, it's going to go down 1. What about horizontal shift? Any transformations inside the function? Yeah, it's going to go to the... So remember, it's what value of x gives you a 0 inside here? A -2, so it's going to go to the left 2. Okay, are there any horizontal asymptotes on this function? Remember, horizontal asymptotes are for the exponential function, so none. And what about vertical asymptotes? Yeah, our vertical asymptote shifts the same as the horizontal shift, right? So we're shifting left 2. So here's our horizontal or our vertical asymptote. It's always the equation x equals whatever your horizontal shift is, or again, whatever value of x would give you a 0 inside your function. So we get x equals -2 as our vertical asymptote. All right, so once we find this, what we would then want to do is jump all the way down to the x-intercept. This is going to give us a picture of what our graph looks like. Okay? And it also shows the one thing that we haven't gone through yet. How do you find the x-intercept? Well, the x-intercept exists when what value is 0? X's or y's? The y's are zeros, right? So if we plug in a 0 for y, so if we just plug in 0 for y, and then we write our log base 3 of x plus 2 minus 1. And then we solve for this variable. So the way that we solve is we isolate our log expression. So we're going to add 1 to both sides. That gives us 1 is equal to log base 3 of x plus 2. And now what we're going to do is we're going to rewrite this in the form of an exponent. So we take the base of our log becomes the base of our exponent to the power of 1 and set that equal to x plus 2. Okay, and so here we have, in order to isolate x, we subtract 2 from both sides, so we get x is equal to 3 minus 2 or 1. So the x-intercept winds up being 1, 0. It winds up being the same point as what our original parent function was, but it is getting shifted and moved down. So this did get shifted down and over, but as we draw it, it is still going to come pass through that point. Okay, so once we draw, again, the general tendencies of our graph, we can go back in and answer the remaining questions. The left behavior, it approaches the asymptote as it moves down. So it goes down to an asymptote. Okay, and our right behavior, it moves up or rises to the right. Again, our domain is from left to right. What's the furthest to the left value of our x's? Goes all the way to what our vertical asymptote is, -2. It extends to infinity. It doesn't touch either one of them. And then our range is from the bottom up. The lowest y, it extends all the way down to -infinity. Highest y extends all the way up to +infinity. And again, parentheses indicate that it doesn't touch either one of those. Okay, calculator. Let me just show you here really quickly. I prefer that you do this by hand. I think it's easier to just do it by hand, especially if you have notes directing you what to do. Okay, but if you wanted to take a look at this in your calculator. And you can enter logs on your calculator as long as you have the most updated operating system. Okay, and if that's the case, if you go to your Y editor, so Green Diamond F1, and you type this into your calculator, you can type in, just alpha lock it and type in LOG. Okay, or you can hit Green Diamond 7, kind of gives a shortcut for the log, even though it's not labeled on your calculator, but it does that. Okay, so type in LOG, and when you write a log, you can embed it, or you can put it inside parentheses. You need to start with the expression that's inside your log, so in this case x plus 2, and then place a comma, and then after the comma you place the base of that log. So the log is a base 3. So you're going to take your expression, again, the inside the function first, x plus 2, the base of your function, and then whatever is happening outside your function goes outside this log. And so this is how you would enter this on your calculator. When you hit enter, the display should verify that you have it written right. Log base 3 of x plus 2 minus 1 shows up. And if you view the graph of that, you'll see pretty consistent to what we sketched here. And the one thing that happens, though, when you're dealing with your sketches of log functions is it doesn't show that this is an asymptote. It looks like it ends right here. So it kind of looks like a square root function. But if you were to zoom in on this, you would be able to see that this line does continue to go down here infinitely. And so you do want to be really careful. Like I said, I would prefer that you just do it using the tendencies by hand. The one thing that you might find useful on this would possibly be locating the x-intercepts. And you can do that one of two ways. You could, in the graphing mode, you can hit Math, the F5 tab, select 0, number 2, and then just choose a lower and upper bound. And in order to find your zeros, just as long as your lower bound is in the negative y's, so here it's in negative, so I'm good. I can hit enter. I need my upper bound to be in the positive y, so as long as I keep scrolling until my y's are positive and hit enter. And the point where your y's go from negative to positive is going to be that 0. And so it confirms that 1, 0 is your x-intercept. And the one other way that you can do that as well is from the home screen. You can use the solve feature, F2, algebra tab, select solve, and then type in your function notation, y1 of x, set that equal to 0 and solve for x. And this is going to give you all of the values that would be your x-intercepts. When you hit enter, you see that the answer is 1, 0 for that. Okay, Mia?